Alaska, renowned for its rugged landscapes and natural wonders, boasts over 50 active volcanoes, more than any other U.S. state. However, amidst this volcanic abundance lies an intriguing geological anomaly: the Denali Volcanic Gap. This 400-kilometer stretch between Mount Spur and the Wrangell Mountains puzzles scientists with its conspicuous lack of volcanic activity, despite all geological indicators suggesting it should be a hotbed of eruptions. The Denali Volcanic Gap, named after North America's tallest peak situated at its center, presents a fascinating case study in plate tectonics and volcanic formation. To understand the mystery of this gap, we must first explore the typical conditions that give rise to volcanoes in subduction zones. Volcanic formation in subduction zones. Volcanoes commonly form along the boundaries where oceanic tectonic plates subduct beneath continental plates. This process is fundamental to the creation of volcanic arcs worldwide. As an oceanic plate descends into the Earth's mantle, it carries water trapped within sediments and minerals. The increasing temperature and pressure at depth cause this water to be released into the surrounding mantle rock. The introduction of water into the mantle has a crucial effect. It lowers the melting point of the rocks. This allows for the formation of magma at temperatures lower than would typically be required. The less dense magma then rises through the crust, eventually breaking through the surface to create volcanoes. The key ingredients for this type of volcanic activity are a subducting plate rich in water, subduction to a depth of approximately 100 kilometers, suitable conditions in the overlying crust for magma to ascend. The Denali Gap Paradox. The Denali Volcanic Gap appears to possess all these necessary elements. Geologists have confirmed that the Pacific Plate subducts to depths exceeding 150 kilometers beneath this region, well beyond the threshold typically required for volcano formation. Moreover, this same plate successfully generates volcanoes on both sides of the gap. So why does this particular stretch remain volcanically dormant? To unravel this mystery, scientists have focused on identifying unique features of the Denali Gap that distinguish it from other subduction zones. Their investigations have revealed a significant geological structure beneath the gap: the Yakutat Terrane. The Yakutat Terrane, a geological speed bump. The Yakutat Terrane is a seafloor plateau that began subducting beneath North America about 10 million years ago. This massive structure, laden with sediments from an ancient tectonic collision, acts as a colossal speed bump on the subducting Pacific Plate. Its presence dramatically alters the geometry of the subduction zone in this region. The Yakutat Terrane's buoyancy causes what geologists term flat slab subduction. In this scenario, the angle at which the Pacific Plate descends into the mantle is much shallower than typical. This flatter angle means the subducting plate takes longer to reach the depths where temperatures are high enough to release water and initiate magma formation. Hypotheses explaining the lack of volcanoes. The dehydration theory. One hypothesis suggests that the slow, shallow subduction caused by the Yakutat Terrane allows the Pacific Plate to completely dehydrate before it reaches the critical depth for magma formation. If the plate loses all its water at shallow depths, it wouldn't be able to trigger melting in the mantle even when it eventually reaches greater depths. However, this theory is challenged by evidence of recent volcanic activity in the region. The Buzzard Creek area, for instance, features lakes that originated as volcanic craters merely 3,000 years ago. This indicates that magma formation is still possible, albeit infrequent, in the Denali Gap. The trapped magma theory. An alternative explanation posits that magma is indeed forming beneath the Denali Gap, but is unable to reach the surface. Several factors contribute to this scenario. A thick continental crust. The continental crust in this region is exceptionally thick, potentially acting as a barrier to rising magma. However, this alone doesn't explain the lack of volcanoes, as other areas with similarly thick crust, like Bolivia and Tibet, still manage to produce volcanic activity. B. Cooler mantle. The flat subduction caused by the Yakutat Terrane results in the Pacific Plate cooling the mantle over a broader area. This cooler environment reduces the overall amount of magma produced. C. Dispersed magma accumulation. The shallower subduction angle causes magma to accumulate over a wider area beneath the crust, rather than concentrating in specific locations that could lead to volcano formation. D. Crustal compression. The subduction of the Yakutat Terrane has compressed the North American crust, likely closing potential pathways for magma to reach the surface. This compression is also believed to have played a significant role in the rapid growth of the Alaska Range, including Mount Denali, over the past 5 million years. Recent evidence supporting the trapped magma theory. A 2023 study provided compelling evidence for the presence of trapped magma beneath the Denali Gap. Researchers deployed over 300 geophones, seismic recording devices, at 1-kilometer intervals across the region. For a month, these instruments recorded Earth's vibrations, allowing scientists to create a detailed picture of the subsurface structure. The study revealed an area 12 kilometers beneath the gap where seismic waves travel approximately 15% slower than in surrounding regions. While this anomaly could have multiple interpretations, the researchers believe it most likely indicates the presence of a magma reservoir. The compression from the mountains above appears to be keeping this magma trapped, unable to reach the surface. Implications and future outlook. The Denali Volcanic Gap offers valuable insights into the complex interplay of geological processes that shape our planet's surface. It demonstrates how unique tectonic configurations can disrupt expected patterns of volcanic activity, even in regions where all the typical ingredients for volcano formation are present. While the evidence suggests the presence of trapped magma beneath the Denali Gap, it's important to note that this doesn't mean the region is on the brink of an eruption. For volcanic activity to resume in this area, significant changes would need to occur in the subduction dynamics. The flat subduction would need to transition to a steeper angle, a process that would likely take millions of years. Conclusion: the Denali Volcanic Gap remains a fascinating geological puzzle, showcasing the complexity of Earth's tectonic processes. The interplay between the Yakutat terrain, flat slab subduction, crustal compression, and potential trapped magma creates a unique scenario where expected volcanic activity is suppressed. This case study highlights the importance of considering regional geological peculiarities when studying large-scale tectonic processes. It also demonstrates how seemingly anomalous features can provide valuable insights into Earth's dynamic systems. As research continues, the Denali Volcanic Gap will undoubtedly continue to intrigue geologists and offer new perspectives on the formation and distribution of volcanoes worldwide. While Alaska's volcano count may be missing a few expected entries, the scientific discoveries emerging from this gap are proving just as valuable as any eruption.